Hi everyone, it's Miss Stang here. I want to show a little demonstration about how the PHET radiocarbon dating game works, and let's get started. Okay, so before we start on the simulation itself, I want to take you into a little more detail about how and where carbon-14 is found, its purpose. Okay. So it all originates in the form of nitrogen-14. So nitrogen-14, nitrogen has 7 protons. So the 7 on the bottom here shows the number of protons, and that's in every single nitrogen. Okay, every single nitrogen has 7 protons. Okay, and the 14 represents 7 of the protons plus 7 neutrons. This is its weight. Okay, so after that is our cosmic rays in space collides with our nitrogen-14, and when that happens, carbon-14 forms. So carbon-14 forms, that's the one we're most interested in because this is the one that's used in the process of radiocarbon dating. However, only a minuscule percentage of it is carbon-14. The rest, as you can see, is 99% of it is carbon-12. So carbon-12 is the one that we commonly see, which is the one that's found most often, right? And then 1% is carbon-13. So all carbon has 6 protons, as shown here, but the number of neutrons changes. So here, the number of neutron is 6. Here, number of neutrons 7, and here it's 8. Okay, so you know carbon dioxide is absorbed by plants. Plants are eaten by animal. Remember glucose. So we're constantly bringing in carbon into our bodies and expelling it as waste, and that gets into the ground. So it's just a constantly cycle of carbon. So remember back to the carbon cycle. Okay, but when an organism dies, all the cellular process comes to a halt. So it stops. So when this cow dies, this cow is not going to take in any more carbon from anywhere because it's dead. Okay, so no new carbon-14 can be found. So all of that carbon that was in this cow is locked. It's not going anywhere. As soon as it dies, the carbon-14 will undergo decay. As we saw in our penny activity, some half of it will become nitrogen-14. So originally you started out with carbon-14. Now half of it will become nitrogen-14 in 5,730 years. So that's the half-life of carbon-14. And most elements, radioactive elements, have different half-lives. For carbon-14, it's 5,730 years. Okay, I will now play our simulation. Okay, reset everything. Okay, so first I'm going to play it with carbon. So here, carbon, I'll set it all the way. So this is just the number of carbon-14 atoms, nucleus, and I will let it play. Okay, pause this video and let's take a look at what is changing. What are some things you notice? What do you notice? Okay, I'll play this again and think about what do you notice? Okay, so I'm going to get back to the presentation. Okay, so we just talked about carbon-14. You start out with 0. So you begin in terms of time at 0. When the organism dies, it starts out at 0 years. Okay. And next, this is the first half-life, right? First half-life. So how much time has passed and what percent of the element is carbon-14 and what percent is nitrogen-14? Okay, take a minute, pause my video, and answer that question for yourself. Okay, in terms of how much time has passed, let's look at this part here. So it shows that it's 1 half-life. So 1 half-life. And this looks to be about a little more than 5,000 years. So remember back that the half-life for carbon is 5,730 years. So that's what 1 half-life is. Okay, what about the percent of the elements? Okay, so here on your y-axis, it's showing the percentages. Let's look at carbon. So it started out at 100% when the animal dies. Slowly, as time progresses, it reaches this point. Okay, reaches this point, and let's also look at nitrogen. It also reaches this point. What is that percentage? It's 50%. So after the first half-life, as we were playing around with our pennies, flipping them over, when it's 1 half-life, half of it will be the original nucleus, and half of it will be the new nucleus. So 50% is carbon and 50% is nitrogen. Okay, let's do the same thing for the second half-life. So take a minute, pause, and answer this question for yourself. Okay, so in this part now, the amount of carbon is once again still decreasing. So now it reaches 25%. So this is just a fourth of what we started out with. We started out with 100%, so now it's just a fourth. Okay, and then our nitrogen is now 75%. Okay, so both of these always adds up to 100% because you're not losing the total number of nuclei. Nuclei is plural for nucleus. Okay. So they still add up to each other. As you lose more carbon-14, you're gaining more nitrogen-14. Okay. Answer this question for yourself. What about here? What do you notice? Okay, so at this point, it's no longer 25%, it's below 25%. So 25% is a fourth. So half of 1/4 is 1/8. So this is 1/8 of the original carbon. This means that the top part, this nitrogen, is 7/8 of the original, of the new nitrogen-14. So this is all new. The nitrogen-14 is converted from our carbon-14. Okay, so I'm going to go back to our simulation and let's look at uranium. Okay, so between uranium and our original carbon, so these two, what are some things that we notice? Uranium and carbon, what are some differences? Pause and take a look. Okay, so let's look. So in our carbon-14, it's in years, right? They're all in years. Time is in years. But this is in thousands of years. So every single point here is 5,000 years. But uranium, how has the time scale changed? How did it change? Okay. So here it's now in billion years. So each criteria is 4 billion years. So when you're dating something, something really, really old, would you use carbon-14 or would you use uranium-238? So if you want to date something that's maybe 20 million years old, would it still work if you were to use carbon-14? Or would it be better if you use uranium-238? Okay. Okay, so let's play our simulation. It's very similar to the carbon simulation. Okay, so I want the maximum number of nuclei. Okay, so one thing I want to point out is that in carbon-14, the uranium becoming 0 was much faster than the process. So the process in carbon-14 was much faster than what happened here in uranium. Okay, so remember that. Let's go back. Okay, it's still 0 in the beginning of time. Okay, still 0. And now 50%, 25%, and 75%. Okay, and then calculate this for yourself. How many percent of each nucleus is left? Okay. Now let's move on to the second simulation, which is measurement. Okay, so we are measuring using this thing. It's called a probe, and it registers things. Okay, so that's the probe. It's used to measure radioactivity. Okay, so when is it appropriate to date objects with carbon-14? And when is it appropriate to use uranium-238? So I mentioned this a little earlier. In this simulation, there are two choices of objects. You have a tree or a rock. Okay, so which one do you use for carbon-14 and which one for uranium-238? Okay, when you're deciding which one to use, ask yourself these questions. Was the object once alive? So the tree, once it dies, it will be once alive. So if it was once alive, you would use carbon-14. But if it was never ever alive, like a rock, then you would use uranium. And then how old is this object? So a tree, time can pass and it can get very old. So a fossilized tree, it actually looks almost like a rock. Those are really old. So you might be using a different sort of radio dating method. So if it's less than 58,000 years, then we would use carbon-14. So for a dead tree, most likely we'll use carbon-14. And for our rock, which who knows how old it is yet, which is what we will do in our next activity to test out how old is the rock. Okay, but between 58,000 years and 4.5 billion years, we can use uranium-238. Okay, so why do I have this less than limit here? Think about that. Why do I have a limit less than this many years? Okay, pause it. Give yourself an answer. Okay, we want to use this because at about 10 half-lives, for carbon-14 specifically, dating is now less reliable. Okay, it's less reliable because if you were to take a ruler for yourself or a number line, so from you have 100, you divide it by half, it's 50, and you divide it half and half again. When you end up with 1, you can go 0.5 and then 0.25, and it just goes on and on and on. It will never reach 0. Okay, it can be 0.0001. You can still divide that again by half. So it will never reach 0, but the amount is so tiny that it's very difficult for the machines that's used to date these objects to register that amount. So when it's very little left in the object, it cannot be used. So let's go back to our dating. Okay, so we have, let's plant a tree. Boom, we plant a tree and it dies. So I killed the tree, and this is in years, however many years. Let me put the probe here. There's nothing going on. Why is that? Am I choosing the right criteria? No, I'm not. Why is it wrong? Why is uranium-238 not the right criteria? So pause and think. Okay. I'll reset this. So with our probe, now we see a change. Okay, so it will slowly decrease, and you can play around with this on your own time. Let's have the rock. So bam. Okay, here's our rock. Carbon-14, it's not registering. Why is that? Let's try uranium. Okay, it should start out at 100%. Let's reset this. So it starts out at 100%, cools down. Let's look at the number of years on the bottom, moving quickly now, and it has that decrease, and it shows the percent of the element remaining. Okay, so we can play around with that part. Okay, but let's talk about our homework, okay, which is the radioactive dating activity. So everyone will have some sort of a job. So the scribe will be the one who makes a copy of the document, which looks like this, and it's in our Google Classroom, so it's in classwork. Radio dating simulation, and it's this document here. Okay, so the leader or whoever it is, for each one, they will do their table. So your group will have one document, one shared document. Okay, the scribe will make this activity document and turn it in when you're done. Okay, let's move back. Okay, so we're on the dating game. Okay, so as a reminder, if you do not have a scribe, then whoever the VIP is will take the position of the scribe. You will still do your VIP for objects, okay? But you will make the document for your group. Okay, we have listed the objects. So you will only be doing your own 4 objects. Don't do anyone else's objects. You're only doing your own. The dating simulation is hyperlinked to this document that you can click on. Okay, let's move back. So this is a living tree. How old do you think a living tree is? Okay, so in this document, your object is a living tree. And we are using carbon 14 right now, and it shows that it's 100%. This part here scrolls around and it shows the percentages up on top and the number of years on the bottom. So if we scroll to 100%, it's 0 years. We'll plug it in. Ding. And check it. So it's 0 years old. Okay, let's randomly choose a different one that we can play around with. Let's do the fish fossil. Okay, remember about relative dating. So generally, the older something is, the closer it is to the very bottom for living things. Okay, so for our fish fossil, uranium has 0%. It doesn't register anything. Carbon 14 doesn't register anything. Let's try uranium-238. Still 0%. That's weird. Okay, it might work for other things. See, like this one, you can see a percentage with uranium. Okay, let's go back to our fish fossil. Let's now try custom. So within custom, there are a few options. 100,000 years, 1 million years, so it's still not showing up. 10 million years, 14.4. And 100 million years. Okay, so it shows up for both 10 million and 100 million. So you can choose either one of them. However, if your percentage is less than 10.9%, let's go here, 10.9%, whatever is below 10.9% goes back to what we said before, more than 10 half-lives, it becomes unreliable. So when it goes under 10.9%, it becomes unreliable and we won't use the data for it. Okay. Let's go with 82.4. So we'll scroll until we see 82.4. Almost there. Okay, close enough. 82.3, and it tells us it's 28.08 million years. MY is million years. Okay, let's plug that in and check it. So we cannot put in 28.08 million years. This is not good. We cannot use this. It will be red like that. Okay, so that's not gonna work. So let's try it again. We cannot have letters, so therefore we cannot use commas in here either. So you have to write out the whole thing. Also, you can round it. So 28.08 rounds to 28. And million is 1, 2, 3, 1, 2, 3. Let's check it. Ding. Okay, so now it works. It registers as 28 million years. Okay, so in our table, you will put in the type of radioactive type. So here is custom with a half-life of 100 million years. You'll say that here. Percent element remaining is 82.4. And the last section, age of the object, is what you plugged in here. And we'll check this answer in our next class to make sure you are getting it right. Okay, so remember, only do the part that is for your role. Don't do anyone else's role. Okay. So for the scribe, please turn it in. And also remember to do the correction, which we will do in class. Okay. You will get a bonus point if everyone that came to class finished their part. So if you had 3 people in your group and everyone showed up that day, you will get 1 extra credit point if you finish this entire the part that is relevant to you. Okay, hope this helped, and I will see you all in our next class. Bye.